So if we have a mass spec problem, how do we know? Let's say you have something like this, and it gets hit with the electron beam, and they say we end up with a fragment. We have a fragment that weighs 43. Can you draw me that fragment? Can you tell me what fragment that is? That's the question. Let's take some time and see if you can draw that fragment. So, some strategy to this to find the fragment that's 43. We know it has to be a plus charge fragment because our detector only sees plus charge things. Plus fragment, right? First strategy I would do is I would number these carbons. 1, 2, 3, 4, and 5. And when we break up molecules in mass spec, we always want to look for stable fragments. So what are some plus charge stable fragments? What's the order? Tertiary carbocations are more stable than secondary, which are more stable than primary, right? So what bonds can we break between these carbons to get secondary carbocations versus say tertiary versus say primary?
2 to 4, 3 to 2.
So we could break 2 to 4.
2 to 3.
So if we go 2 to 4, what are we going to end up with? We're going to end up with. So we'll put a plus charge on the secondary carbon and put the radical here. If we do, what's the other one you said? 2 to 3. If we do 2 to 3, right, we'll end up with a plus charge here and a CH3 dot. Let me number the carbons again for you. 1, 2, 3. This is 4 and 5. Here is 1, 2, 3, 4, and 5. So those are two probably most likely fragments to make, right? Because they form secondary carbocations. Are there any other ways to form a secondary carbocation? What if I broke between bonds 1 and 2? But is that the same as breaking 2 and 3? Yes, right, same. So here we are. We need to find a plus charge fragment that weighs 43. So are any of these fragments that fragment? Which one?
Fragment 2 to 4.
2 to 4 is indeed the fragment that weighs 43. So the first step, right, is just to lose 1 electron. But if you ask you to find a fragment, you just got to find the fragment that makes sense for the weight, the mass.
So if you have lone pairs, it's always one of the lone pair electrons.
What's the easiest thing to knock off? An electron in a bond or an electron in a lone pair? Lone pair electrons always the easiest to knock out first. Lone pair electrons always get knocked out first. Absolutely. So another mass spec question about heterolytic and homolytic cleavage, or heterolytic and homolytic cleavage. So heterolytic cleavage and alpha cleavage, essentially, right?
Yeah.
So draw our lone pairs in. Right. So the first thing that happens when we hit the electron beam, like we just talked about, is it easier to knock an electron out of a bond or out of a lone pair? Lone pair. So now our chlorine is going to lose one of its electrons. So we can put a little plus charge there. Good. Now there's two things that can happen at this point. There's two different ways this molecule can break up. One's called a heterolytic cleavage. The other one's called an alpha cleavage. Right? Which one's the most likely, alpha or heterolytic? Heterolytic is probably more likely. Let's look at why. Right. So in heterolytic, what do we mean by heterolytic? That means we're moving 2 electrons in the same direction at the same time. Heterolytic means 2 electrons at the same time. There they go. This is a heterolytic cleavage. Right? I always like to number my carbons just to make sure I don't lose any. You can't lose carbons. It's one of those things. Right? So the bond between carbon 2 and chlorine broke. So who has the plus charge now? Where's the plus charge at? It's on carbon 2. Very good. How many electrons does chlorine have around it? 7. Right? Some people want to say 8. It's not 8. Right? Why not? Because we can look here. We say there's 1, 2. There's 2 lone pairs right there, right? 3, 4, 5. If it gets these 2 more electrons, it's at 7. Right? How many valence electrons does chlorine normally have? 7. So it's uncharged. It's happy with 7. So let's draw those 7 electrons in. So that's heterolytic cleavage. This is nice because do you think the chlorine wants to have a plus charge as it has before? No, chlorine's really electronegative. It doesn't want to have a plus charge. So what's the other breakup we can do? Actually, I'll tell you what I'm going to do. I'm just going to put this over here, and I'm going to redraw this hitting the electron beam. Dot plus. Draw my lone pairs. Now we're going to do this alpha cleavage. So what happens in an alpha cleavage? What do you mean by alpha? I mean, remember what alpha stood for? It means what? You said it. You had one electron. So it's going to be a homolytic cleavage, right? Electrons are going to go different directions. Like a pair of electrons and a bond are going to go different directions. So it's a homolytic cleavage, and it involves this alpha bond, right? The bond next to the carbon-chlorine bond is considered the alpha bond. Right? It's the first bond away. So this is considered the alpha bond here. It could be the lower one too because it's symmetrical. If it's not symmetrical, you have to make a choice. And we'll look at that in a second. So let's draw the electrons in. Doesn't matter which one we choose. Let's do number our carbons. 1, 2, 3. Draw 2 little lone pairs in. Right? Now, just like we talked about, it's a homolytic cleavage. So what kind of arrows do we use? Do we use double-headed arrows like we did over here? We use the fish hooks. Good. So 1 electron from this chlorine, right, which lost 1 electron, is going to move. Electron between carbon 1 and 2 is also going to move towards that. And the other electron between carbon 1 and 2 is going to go on to carbon 1. So what bond was what bond was broken here? Between what 2 things? Carbon 1 and 2, there's a bond broken. And do we form a bond?
Yeah.
What bond do we form?
A double bond.
Ah! We formed a pi bond. A double bond consists of 2 things. A pi bond and a single bond. We formed a pi bond. So we say CH3 dot, and that's carbon 1. We say here's carbon 3 and 2. Oops. Here's the Cl. Right? And there's a new pi bond between those 2. Where's the plus charge at? Plus charge still in Cl. Are there still lone pairs in the Cl? Still 2 lone pairs, right? Good. Why is this less likely to happen?
Chlorine doesn't have a plus charge.
Chlorine probably doesn't want to have a plus charge, right? So this is maybe less likely to happen than the heterolytic cleavage. But it still happens. We still see this. If you saw this in a mass spec, how do you know if there's a chlorine in your molecule? Chlorine has the 35 and the chlorine 37, so we see that 3-to-1 ratio, right? In our molecular ion. If there's a chlorine there, we'll see a 3-to-1 ratio. What do you see if it's a bromine? 1-to-1 ratio of bromine 79 and bromine 81. Good. Questions on this? So we're looking at number 2 from 10, 21, 13, more spectral problems. So what it gives us, it says C10 H12O. First thing you do at this point is what? Do your degrees on saturation. I will save you the pain of watching me do this math. What is the degrees on saturation? 5. So what do we know? If it's more than 4, what should we say to ourselves? That's not what we say.
Ding, 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 benzene.
We say ding, 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 benzene ring. Right? We don't say just benzene ring. We say ding, 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 benzene ring. Ding, ding, ding. Benzene.
You skipped a ding.
Ding. Ding, ding. Oh, very good. Right? More than 4. More than 4 degrees on saturation, we should be thinking about benzene ring. How many degrees on saturation are wrapped up in a benzene ring? 4. Right? Because a benzene ring has, right, a ring, and then how many pi bonds? 3. So that's at least 4 degrees on saturation right there. Right? So everybody's with me on the DU, calculating that? You got the benzene. We thinking there's going to be a benzene ring here? Let's look at what the IR tells us. What does the IR tell us? So the IR stretches we have are 3024. We got one at 2936. Another one at 1609. Another one at 964. So what do we got from the IR? What does 3024 tell us from the IR?
SP2CH.
We have this one will tell us we have some sp2 CH stretches, right? Which makes sense. If we have a benzene ring, we're going to have some sp2 CHs. What does a 2936 tell us?
SP3 CHs.
Tells us sp3 CHs. Notice how it's important to say sp3 or sp2, right? Those are different types of bonds, right? Different bond lengths. What's 1609 tell us?
For the benzene ring?
It could be part for the benzene ring. What else is 1609 tells us C double bond C stretch. So remember, be careful with IR. IR doesn't, alone by itself, it can't do it all, right? Just like any type of spectral information, right? We need more than one piece of data, one type of data. So I think 1609 tells us there's a C double bond C, right? What does 964 tell us? Now, see, the thing is, what I want to see is have your tables out, because that's what you're going to have in the test, right? You might as well practice like you play, all right? So make sure you have that table out. So 964 tells us tells us there's an alkene. What kind of alkene? A transalkene.
Why would the bottom one with a terminal
What number is it for terminal?
990 to 910?
Is it 990 and 910? And it means both. So that's why it's not a terminal, because it doesn't have both of those stretches. Whoops, I did this wrong. Who's paying attention? Right, so we know this from the IR. Right? We have sp2CHs, we have sp3CHs, we have a C double bond C, and we think that C double bond C is trans. Alright? So far so good? So if we know, now looking at the IR, we know we have a double bond, an alkene. So that would account for our final, right, our 5th degree of unsaturation. So that accounts for that. So have we satisfied our 5 degrees of unsaturation? Yes, we have. Let's see. For NMR, for HNMR, what do we know?
In the first two, you could look at their aromatic hydrogens.
We have two things. We have a peak at 7.21. That's for 2 H's. That's a doublet. Just wall this off a little bit. What else do we have? We have another one at 6.8. That's a doublet worth 2 hydrogens. We have a peak at 6.29. That is 1 H and is a multiplet. So multiplet means you're being split by what? What happens in a multiplet? Two different types of neighbors, right? 2 different types of neighbors. We also have a peak at 6.07. That is worth 1H. That's a doublet. We have a peak at 3. We'll round that one up, 7.3. 7.29. That's worth 3 H's and is a singlet. And we have another peak at 1.82. That's worth 3 H's and is a doublet. So how many different types of peaks do we have here? How many different types of protons do we have? We have 6, right? So I'll write that down. That's something I'd write down. What would make this a lot easier? If I gave you what other piece of information would make this easier? The coupling constant would make this a lot easier, right? If I give you the coupling constants, right? If I have the same coupling constant as somebody else, what does that mean about us? We're near each other and we're coupled, right? So that might have been helpful too. So 5 degrees on saturation. Got the benzene ring, ding, ding, ding. Benzene ring, 4 degrees there. IR tells us we have sp2CHs, have sp3CHs. Tells us we have an alkene. Tells us we have a cis or a trans alkene. That alkene will cover that final degree bond saturation. That's set up. We look at our NMRs. We got 6 different types of protons. It'd been really nice if I gave you the coupling constants. I sure didn't. We can still figure it out. So, pull this up a little bit. How do we want to approach this problem? What's the first thing we could do? So we know there's what? So I always like to draw the pieces in. So what do we know is here? We know there's a benzene ring. Now this benzene ring, as it's drawn right now, has how many hydrogens on it? 6. How many aromatic hydrogens are in our product? 4. Does everybody see that? Right? 7.26, 7.21, and 6.8 are in the aromatic region. That means we have 4 aromatic protons. So this benzene ring has to have how many things also bonded to it besides hydrogen? 2 different things, 2 different substituents of it. Right? So we have four total aromatic protons. How many types of aromatic protons do we have?
2.
There's just 2 types. So what kind of substitution should we have on the benzene ring? To get only 2 types of protons, how am I going to have to draw where the H is going to have to be to only have 2 different types of protons? Symmetrical or basically trans or 1,4 we say. So we say something's going to have to be here, something's going to have to be here, and this H and this H are going to be chemically equivalent, and this H and this H will also be chemically equivalent. Do you see that? How is this H going to be split into what? It should be split into a 1, 2, 3. 1 nearest neighbor, it should be a doublet. Do we have a doublet? Worth 2 hydrogens. Excellent. So another thing I like to do sometimes is if you label this as A, these guys can be B, these could be C, D, E, and F, right? So we can kind of keep track of our protons, right? Make the top ones HAs, make the bottom ones HBs. Cool. So you can check those guys off right now. Let's go to 6.29. What else do we know? What other piece do we know is in this molecule for sure? From the IR, it told us what is in there. The trans alkene, right? So we have that trans alkene. We don't know what's over here, right? So that trans alkene. Remember that from the IR? Remember we had that? Oops, look at that. That's exciting. Why did that happen? Okay. The IR, we had transalkene 964. Told us we had transalkene. So we have transalkene. What was our molecular formula? C10H12O, right? Another thing that's sometimes helpful to do is to subtract out the pieces as you form them to make sure you don't miss an element. So what does this whole thing count for? What should I subtract from this? C6H4. So that gives me C4H8O. What should I subtract for the alkene piece? C2H2. So I'm down to C2H6 and an oxygen, right? What two protons did I knock out when I made that transalkene? So I've already used A and B. What other two protons must have I used as well? C and D, right? So here's C and here's D. You see that? This is worth 1H, it's a multiplet. This is worth 1H, and it's a doublet. But they're right in that vinylic region, right? And you look at your table, from 5.5 to 6.5 is that vinyl region, where the hydrogens are right off the double bond. So those match up. Okay, so now we should be able to check off C and D, but it is important to note, I don't know if this is B or this is B, right? It's just arbitrary right now. So D and C is the same idea. I don't know which one's which. It's just because I don't know what's here yet, or here, or here. I'm just drawing the pieces in. So we've gotten A, B, C, and D done. Now we need the one E at 3.73. What with 3 H's in a singlet, what's that going to be? A CH3. And do we know what's behind that yet?
It's a singlet.
It's a singlet, so how many nearest neighbors does it have?
0.
So it has 0 nearest neighbors, and it's at 3.73. What comes at 3.73? Look at your table.
Or I mean, something bonded to an oxygen nitrogen.
Something bound to an oxygen, nitrogen, and halogen. Do we have any nitrogens in this molecule? So maybe putting the oxygen here would make sense, right? Because that would make sure this is de-shielded at 3.73 downfield. And does oxygen have any hydrogens on it? No. So we go back to our little table. Now we can subtract CH3 and an O. What are we left with? Another CH3, right? So the CH3 from the next to the oxygen, we'll say these are E. So that checks that off. And all we have left is a 1.82 peak, right? That needs to be a doublet, right? So that's a CH3. It has to be a CH3, and what's it going to have to be next to?
H is next to a carbon, it's bonded to a carbon, it's double bonded to another carbon.
But it has to have one nearest neighbor, right? To be a doublet, you have to have how many nearest neighbors? 1. All right. So well, I know that this is a doublet, right? How many nearest neighbors must I have to be a doublet? So I have to be next to a CH, right? I have to be next to a CH. I did as an extra one, just trying to figure out the piece. So I did add an extra hydrogen here just to emphasize that this has to be next to a CH. So for my current pieces, where is a CH next to it? And also don't forget the frequency is 1.82. What's at 1.82 on your table? It could be allylic, which means it's next to a double bond, right? So where should I put this CH3, this F? Should I put it one of those? So I would put it right here, right? Okay, so now at this point, let's just start piecing this whole thing together, right? So we said,
I have a question.
sure, right, so, yep. So, we have transalkene, aromatic ring, an OCH3, we have a CH3 that has to be next to a doublet, so we put this CH3 right next to the alkene, because we knew it's at 1.82, which is right in that allylic region on our chart. We also knew the CH3 needed to be coupled to an H, right? So we put it there. So only have one site left. So what have we covered? So we've checked off this piece. We still have the aromatic ring, which has 2 places, and with the OCH3. So there's only really one other way to put this together, right? What has to go where? Where does E have to go to? This piece. If I put E right here, I can't put all three pieces together. You have to put this E on the benzene ring, right? So let's draw the final product. We're going to put this O methyl right there. Right, O methyl. We're still missing, what do we need to put here on the other side of the benzene ring? So we've checked off this piece. And the other side of the benzene ring, we still have two open sites, right? We have an open site here and open site here. We got to put them together, right? And we got to make sure we draw our alkene to be cis or trans. Trans, right? So the methyl group goes there. If I told you a 15 Hertz coupling constant, you'd know, right? This trans, 10 it's cis.
Is 17 also?
17 is close, yeah. So, questions on any of this so far? How we piece this all together, right? Again, though, the whole point is getting this is probably worth 2 or 3 points. Getting the final answer with 2 or 3 points. Showing all this other stuff, right? All this other stuff is really important, right? Showing us how you think. Show us your thought process. Okay. Let's look at the UVVis questions from exam 2 from 2012. It is number 2. So it's asking us what kind of molecular structures are needed to make UVVis useful. So for UVVis, what do you need to have? You need to have pi bonds. What happens in a UVVis experiment? What happens? UV light hits the molecule, and what happens? What goes from where to where? The electron, right? The electron goes from a bonding orbital, pi bonding orbital, to a antibonding pi star, right? If you have, what can make that transition easier? Or with what makes that transition take less energy? Conjugation does.
So it can still occur with just pi bonds?
It still can occur with just one pi bond. So conjugation makes energy needed lower to go from pi to pi star. How do you know for wavelength, which kind of wavelength is higher in energy? The long wavelength or the short wavelength? Short wavelength is higher in energy. So more conjugation, what's going to happen to the wavelength? It's going to have to get longer or shorter? So if I have more conjugation, does it make it easier or harder to go from pi to pi star? Makes it easier. So the wavelengths we're going to use are going to get longer or shorter for that? Longer. So longer, what is it? Wave. I draw that always wrong. So the longer wavelengths. Okay? Why are some things colored? They absorb visible light. What does that have to do with UVVis? Lots of conjugation. So lots of conjugation. Right? What's higher in energy? UV light or visible light? UV is higher in energy. What has longer wavelengths? UV light or visible light? Visible light has longer wavelengths. So eventually, the pi to pi star gets so very small that you're in the visible spectrum, and then you have colors. Because pi to pi star then is going to be very, very small, and the wavelength has gotten long enough that it's visible light wavelength now. So one example from the homework was, this was in the homework in chapter 14, I believe. Right? Comparing these two compounds. So if we look at A, and we look at B, which one's going to absorb at a longer wavelength, A or B? A longer wavelength. Which one's more conjugated? A is more conjugated, right? Because oxygen can be part of the pi system. Right? Be part of the conjugated system. This lone pair is going to be part of the conjugated system. So all you do is simply, right, here's 1, 2, 3 versus 1 and 2. When things are conjugated, there's no sp3 carbons in the way. Right? Notice we go from sp2 here to sp2 here. sp2 to a lone pair, which counts, to another sp2. So this whole system is conjugated.
What did you say A was? Longer?
A had a longer wavelength, right, because it's more conjugated. All right? That's wavelength sign, right? More conjugated. Gated. Right? That's like 14 in chapter 14, I think. 12, maybe 11 or 12. So, is this from the practice exam? So why does a tertiary carbon more stable when electron deficient? Oops. When electron deficient. So why is a tertiary carbon? It is, a tertiary carbon is more stable when it's electron deficient versus a secondary and primary. Right? So the written question is that. This is the picture question. Why is this the most stable? So it comes back to a chapter 2 question. What's the hybridization state of a carboxylic cation? sp2. You all should have said that a lot faster. I'll wait. Pause. So let's look at hybridization state really quick here. And it'll help us understand what's the principle going on here. So if you're a carbon and you're electron deficient, you want to be sp2 hybridized. So why is that? Well, if you're sp2 hybridized, first, if this orbital is empty, what's the bond angle from here to here? 90. What's in a bond? Electrons. This orbital is empty. There's electrons in this bond, right? Opposites attract. This empty orbital wants to be as close as possible to that bond. And the closest way to get there is being sp2 hybridized. Right? sp3 hybridized would be different. Right? What's the bond angle in sp3 hybridized? 109. So if this is empty, if this is a plus charge here, right, and say there's an H here, and there are 2 electrons there, what's the bond angle from here to here? 109.5. Which is less, 90 or 109.5? So where would the electron deficient, if you're electron deficient, would you rather be sp2 or sp3? sp2, because if this is empty, I want to be as close as possible to the other electrons. Now let's just pretend, instead of having a plus charge, what if I put 2 electrons in here? Now, do I want to be as close as possible to that bond or as far away as possible? Far away. That's why carbanions, carbons with negative charges, right? Like a C with a negative charge, wants to be sp3 hybridized. Right? Where does a radical fit in? Is a radical, if I put 1 electron in here, does this radical have a full octet? So is it electron rich or electron deficient? Deficient. So what hybridization state would it rather be? sp2. Good. So radicals will always rather be sp2 as well because they're also electron deficient. Right, so they want to be close to that bond too because they're still missing one electron. Okay, so what the heck does that have to do with substitution, right? This has nothing to do with substitution. What it has to do with substitution is when you're sp2 hybridized, you can get close to this H and do something. This electrons in this CH bond can help out this empty p orbital, and we call that hyperconjugation. And that's what's going on here, where this sigma bond can help out and give some electron density to that empty p orbital. Now, are any bonds being broken in hyperconjugation? No. But the more hyperconjugation you have, do you think it's going to make it more or less stable? More stable. We'll look at a tertiary element has 9 adjacent sigma bonds, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's like having 9 little helpers, 9 hyperconjugation buddies. Right? 9 hyperconjugation buddies is better than, right, only having 1, 2, 3, 4, 5, 6. Right? Which is better than only having 1, 2, 3. Right? Remember we don't draw the H's in there, but they're there. Does everybody see that hyperconjugation principle and how we get it stabilized? So tertiary, we have more adjacent sigma bonds. The more of these sigma bonds we have next to it, the more we can help stabilize this empty orbital, or electron deficient orbital. Make sure this orbital is empty. This is a big old plus charge. That orbital is empty. There's a big old plus charge in that p orbital. No electrons. So it wants to be as close to electron density as possible, and all these sigma bonds next door can help stabilize it, and that's called hyperconjugation. And the more hyperconjugation you have, the more stable you can be. Tertiary has 9, secondary has 6, primary has 3. And then a methyl cation has nothing. So that's the really most unstable.